Matrices. So at first, what is a matrix? So a matrix is defined as an ordered rectangular array of numbers or functions. The number or functions are called elements or entries of the matrix. Now the next thing is, we have mentioned ordered rectangular array. So what do you mean by order? So actually the order is the number of rows and the column the matrix is consisting of, and if a matrix is having m rows and n columns, then it can be called a matrix of order m by n or m by n matrix. For an example, if we look at this matrix, it has m rows and n columns. We write at the n bottom right hand side. Generally we write at the bottom right hand side the order, and the number of rows come first, followed by the number of columns, and this is always fixed. So if we talk about the elements of these matrices, of this matrix, then the first element is defined as A11. It is 1 1 because it is the element of first row and first column, means first row and first column. And the next is A12, means the element of first row and second column, and all along here. Then A1n means first row and nth column, and then up to mth row, first row, second row, third row, this is ith row, and mth row, this is am1, means the element of mth row and first column, all the way to the amn, means mth row and nth column, as in the order m by n, means m column and m rows and n columns. In general, we can define it as A equal to aij, where I is where A belongs to ith row and jth column, and the whole over the matrix is of the order m by n. For an example, if we see the matrix B, it consists of elements 3, 4, 5, 6, 5, 0, and so it has 2 rows and 3 columns, so it is of the order 2 by 3, means 2 rows and 3 columns. Now in general, B equal to Bij means the element which belongs to ith row and jth column. For example, here the B11 means the element belonging to first row and first column is 3, means this one. And for example, another one, B21 means belonging to second row and first element is first column is 6, so B21 equal to 6. Now we come to the types of matrices. In the types, first one is column matrix. Now a column matrix is a matrix which has only one column. For example, A equal to 2, 3, 1. It has 3 rows, but it has one column, so it is of the order 3 by 1, and we can write it as general form of it is Aij to the order m by n, because the column is fixed, so we can write 1 over here. And the next type is row matrix. In row matrix, the matrix consists only of 1 rows, doesn't matter how many columns it contains. The general row is the general form is Aij into the order, means order is 1 by n. As the row is only 1, so we fixed the number of rows, that is m by 1, and n is the number of columns that can be infinite, or up to which the matrix you want to make. Square matrix. If in a matrix the number of rows and the number of columns are equal, then the matrix is said to be a square matrix. Then for example, this A is And square matrix is which consists of 3 rows and 3 columns, and the general form of the square matrix is A equal to Aij, where A is the element belonging to ith row and jth column and is the order m by n, and in this case m is equal to n, as in square matrix the number of rows and columns are equal, should be equal, sorry, must be equal, whatever. Then the general form, so as m is equal to n, A is equal to Aij, we can replace n by m, so m by n. And then comes diagonal matrix. A square matrix is said to be a diagonal matrix if the element other than the diagonal elements are all 0. What does it mean? Is it is 6. Only the diagonal elements of a matrix should be non-zero, other than all elements that other than the diagonal matrix should be 0. If this condition is satisfied, then we can call a square matrix a diagonal matrix. So then scalar matrix, we can call a diagonal matrix a scalar matrix if its diagonal elements are equal. Means if a scalar matrix is a type of diagonal matrix, we can say, and if the elements of the diagonals are equal, like in B is a 2 by 2 matrix where A11 and A22 are equal, and C is a 3 by 3 matrix where A11, A22, A33, means all the diagonal elements are equal. So to be a scalar matrix, first it has to be a diagonal matrix, and its diagonal elements has to be equal. And same in the previous case, for matrix to be a diagonal matrix, it should be an square matrix. Now on to the next one, we have identity matrix. For a square matrix in which the elements of the diagonal are all 1 and the rest are all 0 is called an identity matrix. It means that if a matrix is a square matrix, means the number of rows is equal to the number of columns and the diagonal elements are all 1, then we can call a square matrix an identity matrix. Then comes zero matrix. A matrix is called a zero matrix, or null matrix when all the elements of the matrix is 0. Now, equality of matrices. Suppose two matrices A equal to Aij and B equal to Bij of order, suppose it has to be of same order, m by n, and this also be m by n. So they are equal only if they are of same order, as said, m by n, and each element of the matrices are equal. Means if A11 should be equal to B11 and A12 equal to B12, like this. For example, we have a matrix A equal to 2 3 5 2 and B equal to 2 3 5 2. So here A11 equal to B11, that is 2, A12 equal to B12 equal to, that is equal to 3, and rest all are same, as you can see. So we can conclude that A equal to B. Now before coming to symmetric matrix, we should know some more things, that is addition of matrices. If we are going to add two matrices, then the corresponding elements of the matrices are added. For example, if we want to add A and B, then we can write A plus B is the A in the A matrix, the A11 element, and the B in B matrix, the B11 elements get added, means the corresponding or adjacent element gets added up, and for example then A12 plus B12 gives 6, then A21 plus B21 gives another 6, and 22 A22 and B22 gives 5. So the resultant matrix is formed is 7 6 6 5. Means the summation of A11 and B11 will give the A11 position of the resultant matrix, and same goes for all others, and the same rule is followed by the subtraction. Now if we come to the properties of addition, it follows commutative law, that is we can write A plus B equal to B plus A. It follows associative law, that is it can be written as A plus in bracket B plus C equal to A plus B in bracket plus C. Now we come to additive identity. Suppose A is a matrix of order m by n and O be a null matrix of order m by n. So A plus 0 is equal to 0 plus A, because it follows commutative law, and that is equal to A, because the null matrix consists, in null matrix all the elements are 0, so if we add we get the same matrix that we had as if we follow the rule. So 0 so the addition of null matrix with the matrix gives that matrix only. So 0 is, so we can call, no, it is not 0, but it defines null matrix, or 0 is that we can call it the additive identity for the matrix addition. Then comes the concept of additive inverse. If A is a matrix of order m by n, then another matrix exists as minus A, same as the previous one, with only the negative portion, with minus elements minus ij, and the order is same as previous one, m by n, such that the sum of these two gives a null matrix. Then we can say that minus A matrix is the additive inverse of A. So in simple words, the matrix which upon addition with another matrix gives a null matrix is the additive inverse of the second matrix on to which it is added upon. Then we go to multiplication of matrices. So if we multiply a matrix by scalar, means a constant, suppose we are multiplying a matrix by k, then if A is a matrix consisting of elements 1 2 3 4, then if we multiply it by k, then then the constant k gets multiplied with each element of the matrices. For example, if we multiply k with this matrix, then k turns out to be k into 1k, k into 2 2k, k into 3 3k, k into 4 4k. And when we multiply a matrix by matrix, then the story changes a little bit. Suppose A is a matrix of order 2 by 3 and B is a matrix of order 3 by 2. So the first condition we have to look for before multiplying is the number of columns of this matrix should be equal to the number of rows of this matrix. In this case, the number of columns is 3, and in this case the number of rows is 3, so the multiplication is possible. If this condition is not satisfied, then the multiplication, we cannot proceed with the multiplication. Then after that, if we multiply, it goes like this, means we multiply each row with each column. Suppose 3, we multiply 3, the first element of the first row, with the first element of the first column, then we get 9. Then we will add the second element of first row with, we will multiply the second element of the first row with the second column of the second element of the first column, and we will add with the previous 9, and we will again multiply the third element of the first row with the third element of the first column, and we will add with previously 20 and 9. So this will give the first element of first row and first column of the resultant matrix. Means what I meant to say is, we will multiply each element of the first row with each corresponding element of the first column to obtain the first element. Similarly, we will multiply each corresponding element of first row to each corresponding element of first column of to get the second element of first row and second column of the element of first row and second column. And similarly, if we want to find of the second row, we have to multiply second row element of the resultant matrix. Then we have to multiply each corresponding element of second row with each corresponding element of second column and add it up. Then we will get the things. And when we come to the properties, multiplication of matrices does not follow commutative law. Means we cannot write AB is equal to BA. It is not possible. It follows associative law. Means we can write A into B in bracket into C is equal to A into in bracket B into C. It follows distributive law. We can multiply, means if it is AB in bracket B plus into B plus C, we can split it and write A B plus AC. And same in the case, another case, if it is C into A plus B, we can split it and write AC plus BC. Then we come to the concept, another property, existence of multiplicative identity. For every square matrix A, there exists an identity matrix of some order such that IA is a unit matrix, or unit matrix is an identity matrix that we discussed earlier. Both are same thing. Then IA is equal to AI, as it that is equal to A. Now, in previously we learned that it does not follow commutative law, but I is an unit matrix. So if we multiply with unit matrix, it gives the same matrix A. It will return the same matrix. So in this case, we can write IA equal to AI. Now, transpose of a matrix. Now suppose if there is a matrix A equal to ij mn of order m by n, ij of order m by n, then the matrix obtained by interchanging rows and columns of A is called transpose of matrix A. Means suppose there is consider matrix A which of 2 by 3 order, then we can see in first row it contains element 1 2 3, and in second row it contains element 4 5 6. So the transpose, if we transpose it, then this becomes the first row, this becomes the second row, and this becomes the third row. As we can see in this, a transpose of matrix is defined by AT or A dash, whatever you are comfortable with. Then it becomes 1 4 first row, as I said, then 2 5, then 3 6. And what was the first row in the original matrix becomes the first column in the transpose matrix. Now the properties of transpose is, if we transpose an already transposed matrix, we will get the parent matrix. Means suppose in this case we are transposing this matrix, so we will get the original matrix. This is what is said here, and this is pure scalar multiplication. If we multiply K with the transpose matrix, we get K into A transpose. Means K will get multiplied with each element of the transpose matrix, and then A plus B transpose is equal to A transpose plus B transpose. In this and this I will explain with the example. So before that I'm telling the fourth one also, that is AB transpose is equal to B transpose into A transpose. So when we come to the third point, that is A plus B transpose equal to A transpose plus B transpose, then let us understand with an example. Consider the matrix A equal to 2 3 4 5 2 1, then the transpose will become 2 5 3 2 4 1. And consider another matrix B of order 2 by 3, 2 rows 3 columns, and consider element 1 2 4 3 1 2. So the transpose becomes 1 3 2 1 4 2. So the summation of A plus B becomes